Hey everybody, I wanted to talk a little bit about molecular chemistry today. Atoms bond together to make molecules. Molecules are made of atoms, everything's made of atoms, but sometimes they gang up to make bigger things called molecules. So here is the periodic table that we looked at last time and how all the atoms work. And this table also lets us in on the secret of how these molecules form and what's most liable to happen. Okay, any kind of deal where the atoms can combine to make new stuff makes a molecule. I've got a picture of a molecule down here. This is water. You can see that there's a hydrogen atom, an oxygen atom, and a hydrogen. Two hydrogens and an oxygen. That would be H2O. All right, two hydrogens and an oxygen. So even the molecular name for that, H2O, tells us exactly what's in it. But when we go to the periodic table, we can see why that's what's in it and what's going on. So I wanted to talk about that today and some other stuff about molecules. Now, the first type of bond that we can make here, the first type of molecule, is called an ionic bond. And an ionic bond happens anytime one atom, quote, gives, unquote, an electron or two or three to another atom, and they are bonded together because of that given electron. Okay, sodium and chloride are a really good example. Sodium is over here in the first column. This is a little slice of the periodic table, but there's sodium. You see that it's number 11. It's got 11 protons. It would also have 11 electrons, and let's think about those 11 electrons. Last time we said 2 would fit on the innermost shell, 8 would fit in the second shell. That takes care of 10, all but 1, and that 1 electron is out there on the outermost shell, shell number 3. Sodium is not happy because it's got that 1 electron there, and it would either like to get 7 more or lose that 1. Well, it's a whole lot easier to lose 1 than to gain 7. But over here is chlorine, and chlorine is number 17. And so you can see chlorine right here is on the next to last column. Remember that this last column were the noble gases. They have full outer shells. They're not making any kind of deals. No kind of molecule is ever going to have one of those in it. But this guy, he's got 17. Let's count them up. I've got 1, 2 filling the first shell. I've got 8 more in the second shell. That gets me to 10. I need 8 to fill this shell right here. 1, 2, 3, 4, 5, 6, 7. 10 plus 7 is 17. And there's a hole right there. And chlorine's left going, man, if I just had 1 more electron, my life would be complete. Okay? Well, sodium sneaks up and says, hey man, I hear you looking for an electron. Opens his raincoat and shows him his wares, and they work out this deal. And here's what it turns into over here. Sodium drops down. It sheds that extra electron. The extra electron comes over here and fills up the outer shell of chlorine. Now sodium's happy, chlorine's happy, everybody's happy. Both of these things are pretty bad, nasty stuff. Sodium, you put it in water, it's going to burn and explode. Chlorine gas will kill you dead, right? When you put these two together, they make something new called sodium chloride. Here's the formula for it. I've got 1 sodium plus 1 chlorine makes 1 molecule of sodium chloride, which we call salt. This is table salt. You can take salt back apart and get the sodium, get the chlorine out, but in a process called electrolysis. But this is how it's made, and it makes something totally new. These are kind of like Legos, right? You can take Legos and you can snap them together, and you can make a model airplane, you can make a spaceship, you can make a race car, you can make different things by how many wheels there are, how many wings there are, how many, and this is the same kind of way. how many phosphorus and how many oxygens and how many chlorines do you have? Make up something new. And they snap together, and then you've got a new thing. All right? So that's our first example of an ionic bond. You can see the word ion right there in the front of the name. You see how sodium was balanced? I had 11 protons, 11 electrons, but it gave one away. So now it's got 11 positive charges and only 10 negative charges. That means that it has more positive than negative. It is now a positive ion. So hence the name ionic bond. Chlorine had 17 of each. It picked up an extra electron. Now it's got one more negative charge than positive charges, so it is now a negative ion. But these two ions have charge, and they're held together by that. One time I had an extra guitar laying around the house, and this guy came over, and he didn't have a guitar, and I said, phooey, and I let him kind of have that guitar. I had too many of them, and he didn't have any, and we worked out this deal, and all of a sudden everybody's happy, right? It's the same kind of thing. It's a given electron, or a loaned electron might be a better word. It's going to want it back eventually, but for the time being, everybody's happy. Here's some more examples of ionic bonds. Up top, if I have magnesium and 2 chlorines, that will form an ionic bond. Let's go look at the periodic table. Here's sodium we talked about before. Right next to it is magnesium, and you remember that everything in the first column had 1 electron in the outer shell, and everything in the second column had 2 electrons in the outer shell. So when I take this magnesium, I've got 2 electrons on the first shell, 1, 2, 3, 4, 5, 6, 7, 8. In the second shell, that gets me to 10. It's number 12. So I've got 2 more that are out here on the outer shell, and that irritates magnesium. Meanwhile, chlorine, you remember, was number 17. He wants 1 more. I can't give these 2 electrons to 1 chlorine atom, but if I could find 2 chlorine atoms, then magnesium could pass the first chlorine 1 of those electrons and send the other one over to play at the second chlorine's house. That would make everybody happy, because now he's got a full outer shell. He picked up an extra electron and is full, and this guy lost these 2. That makes an ionic bond right there. You got the symbol here. Magnesium, there's only 1 of them, plus chlorine, you got 2 of them, makes magnesium chloride right there. So that's another example, and but it also shows how the periodic table is really useful. Say, he's got 2, he wants 1. Gonna have to have 2 of these to take up all the slack over there, right? So good stuff. Here's some more. I think you're getting the idea, though. If I take a lithium and a fluorine, lithium is right here, got that 1 electron on the outer shell. Fluorine is right here just above chlorine, so he's looking for 1, and they work out that deal. Right here I've got potassium and chlorine. Potassium is on the first column. Same thing, ionic bond. I think you're seeing a pattern. When I take something from this side of the chart and combine it with something over here, not counting the last column, then I've got myself an ionic bond. Calcium, oxygen. Calcium is right here in the second column. He has 2 electrons. They've drawn those right there on the name. Calcium with 2 electrons. Here's oxygen, number 8. He's got 2 in the first shell, only 6 in the second shell. He's missing 1, 2. You could count it from the side. He's got 1, 2, 3, 4, 5, 6, but he wants 2 more over there. So that's why there's 2 yellow dots left off. But if calcium slips those 2 over to oxygen, so they're now part of his orbit, then calcium becomes a positive 2, a plus 2 ion. Oxygen is a negative 2 ion, but everybody's got a full outer shell. Everybody's happy. All right, so that's all good. This is kind of silly, but I made a list here of some other ionic bonds And you can see there's oodles and oodles of them. These are not all of them by any stretch of the imagination. But I would like you to see a pattern here. Here's cesium bromide. It's got a CS, a cesium. Well, that's right here, first column. Bromide is over here for bromine, and it's on that next last. He wants one, he's got one, deal. Okay, but look at the form of the name. Cesium, that's on the left-hand side, and it's on the left-hand side. Bromine is on the right side of the table. It comes in second, and they've changed bromine to bromide. Look all the way down. Chloride, oxide, sulfide, oxide, fluoride, iodide. So you can see how when you look at a name like magnesium selenide, like calcium oxide, you know exactly what's in there. You've got a calcium, you've got an oxygen, and together that "ide" means that you've got yourself an ionic bond with those. Now, the other kind is called a covalent bond, and this is different. This is where I have atoms, multiple atoms that share pairs of electrons. So it's not that one atom gives an electron to the other atom. Here, it's a sharing, and you can see what's happening down here. Atom A and atom B get together. He wants one more. He wants one more. So they say, hey, let's get together, and the red one is going to count its 1, 2, 3, 4, 5, 6, 7, plus this guy to get to 8. And the blue one's going to go 1, 2, 3, 4, 5, 6, 7, plus the red one there. They kind of slip up next to each other, and they share a pair. That shared pair makes a covalent bond, which is the other kind of bond that we want to talk about here. So you got the ionic, one atom gives an electron to the other one. Right here, the covalent bond, each atom shares an electron so that there's a pair, a shared pair of these valence electrons. Fluorine is an example right there. And if we drew in the innermost ring with the 2 electrons on both of these, then we'd have 2 plus the 7 would be 9. Number 9 is fluorine, and you can see the configuration there, 2 on the inner shell, 7. Well, if we could get to 2, 8, we'd be in nirvana, right? So that's the deal they do. You take a fluorine atom plus another fluorine atom, and together they will make that F2 molecule right there, made up of atoms, and it's a new thing going on like that. Here's some more examples. Here's hydrogen. Here's hydrogen. With 1 proton, it's going to have 1 electron. That's true for both of them. These guys are never going to give up their one and only electron. Hydrogen is not going to run around with no electrons. At that point, it would just be a proton, right? So hydrogen always makes covalent bonds like you see here. But you can see how those 2 electrons get in the middle there, and they are a shared pair which bonds these 2 together, and H plus H equals H2. Here's oxygen. Oxygen is number 8, so there's 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. There's only 6 on the outer shell. It would like to have 8. This guy would like to have 8. Both of them are short, 2. So if they share 2 pairs, this is a double bond. Right there, I've got this is a single bond where there's 1 shared pair. A double bond has 2 shared pairs. You can have a triple bond where there's 3 shared pairs of electrons. That's fine, but that's O2. That's the form that oxygen usually takes with, if it's molecular oxygen, it's usually 2 atoms. There's also a version that has 3, and I think I've got a slide on that. But that's called ozone that we talked about back in atmospheric science. So look back at that if you want. I got one more down here on this. This is HOH. These 2 hydrogens are going to bond with the oxygen. Remember, oxygen wanted 2 more? Well, he's got one, but hydrogen wants one, so that one comes over here and this one comes over here. To me, this has always kind of seemed like two houses. Here's a house and here's a house, and there's a 4-year-old that lives here and a 4-year-old that lives over here, and the moms say, y'all go play together. And then that kind of ties those two houses together. That pair playing here in the middle is kind of like a covalent bond, and everybody's happy at that point. You can see the diagram here. It does kind of scoot everything else around. So with hydrogen, statistically, those electrons will spend more time in the middle. These ones will spend more time in the middle because these are negative. All these other negative guys kind of try to get away from them, those 4 electrons together. You can see the same thing happening here. These two shared, this shared pair and this shared pair kind of scoot everybody else over that way a little bit. But that's a little deeper than we need to go. Here are some covalent bonds. Ammonia is made up of a nitrogen and 3 hydrogens. Let's see if we can find nitrogen. It's right there. Okay, it's 3 columns away from the end. It would like to have 1, 2, 3 more electrons. So if it can find some hydrogens there, then it'll bond up like that. You can see the formula NH3, a nitrogen, 3 hydrogens. Here's hydrogen 2, we already talked about that one. Here's water, we already talked about that one. Not sure why I put all that there again, but that's the way those work. I mentioned double bonds and triple bonds, so here's some examples of that. Here's a carbon atom. Carbon is number 6. If you put the 2 on the inner shell, that leaves 4 for the outer shell. So they've drawn 4 green dots right there around carbon. Well, he'd like to have 4 more. So if it shares a pair here and a second pair there's 2 shared pairs. That makes a double bond with this oxygen, who also wants 2. This guy wants 4, but he's going to get 2 from this one and 2 from this one. And they're each getting 2. So everybody comes out happy here. You can see the illustration of the electrons all happy there. But this is another way to draw it. Those double bars right there would be a double bond. So that's that 2 shared pairs on this side and 2 shared pairs on the right would look like that. Over here, for example, is a triple bond. This is a phosphorus atom, and you can see that there's 2, 8, and 5 in the outer shell. So you got 1, 2, 3, 4, 5. He's got 1, 2, 3, 4, 5. They both want 8. So they need to share 1, 2, 3 pairs. Would look something like that, and we can make a symbol of that with 3 bonds going across there, a triple bond like that. All right. Right here you have diatomic oxygen. That's 2 oxygen atoms that are tied together with a double bond. UV light could break those apart and make individual oxygens. And that one of these oxygens could go find a diatomic oxygen and say, hey guys, will you let me in? And they go, okay. And it makes ozone. There's that O3 molecule right there. You got a single bond on one side, double bond on the other. And so that's just looking at those lines kind of tell you what's going on. Molecules can form in interesting shapes. Sometimes they're straight lines, sometimes they're bent. Water is bent, for example. The oxygen's kind of up and the 2 hydrogens are down, or it rotates around, whatever. But sometimes they make crystals and lattices and all kind of interesting things. Right here you have chlorine and sodium. That, of course, is going to be salt. And salt can make a crystal where you've got chlorine atoms where all the green dots are, and then interspersed with that are the purple dots. You can see that all the dots, all the atoms, are on the corners of the lattices, whereas down here, I've got the corners of the lattice are one atom, and then that red one in the middle is something else. So that's kind of a different shape, a different structure right there. Right here I have 6, 1, 2, 3, 4, 5, 6 atoms all in a bond. Here's a little pyramid kind of thing, a 3-sided pyramid. This is a ball with 60 carbon atoms can make a little shape like that. So all of these structures are very interesting. You know, a lot of the carbon bicycles and I don't know, walking sticks, anything that you're trying to make super light, carbon makes these interesting hollow shapes that are really strong, but they are mostly air, you know, so you can build some neat stuff out of all that. Wanted to talk about chemical reactions. Over here we've got C3H8. That would have 3 carbons and 8 hydrogens. Just take a look at it and see if we can count. The black circles are carbons, so I've got 1, 2, 3 of those. That takes care of the C3. The H8 would be 1, 2 on the back, 3, 4 on the back, 5, 6, 7 on the back, 8 hydrogen white spheres right there. That's what's known as a hydrocarbon. It's made out of hydrogen, it's made out of carbon, and when you put it together, it's a hydrocarbon. These things are usually flammable gases. The one that we have here is called propane, and if you have more carbons with more hydrogens attached on it, that would be a longer one or a shorter one. Gasoline, acetylene, all of those things are, actually I'm not sure about acetylene, but benzene and different gases that butane, I think, is 2 carbons and what would that give me, 6 hydrogens maybe? Anyway, when you burn propane right here, there's a chemical reaction that happens. You take 1 molecule of propane and it takes 5 molecules of oxygen. Remember that oxygen likes to form up 2 atoms right there. So I've got 5 molecules of O2. The number on front tells me how many molecules I have, and then O2 describes each molecule. I've got oxygens, and there are 2 oxygens in that molecule. Got 5 molecules altogether. So you can see there's 10 atoms of oxygen in those 5 molecules in those 2 packs right there. When you burn propane with oxygen, what it's going to make is 3 carbon dioxides, 4 water molecules, and it's going to give off a bunch of heat and light. That is the chemical reaction for propane and oxygen, for burning propane. But everything's got to add up. Remember how we said these were like Legos and you could take them apart and build more stuff? That's what's happening here. We're taking apart the propane and taking apart the oxygen and making some new stuff, but it's got to be the same number of parts that you started with. So count this up with me. We said there are 1, 2, 3 carbon atoms, those black spheres. Over here, when I get done, there are 1, 2, 3 black spheres, 3 carbons on both sides. I started out with 10 oxygens, 5 2-packs, and when I get done, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we also had 8 hydrogens, so they've got to be represented over here somewhere. I've got 1, 2, 3, 4, 5, 6, 7, 8. Everything is there. I took all of these molecules apart, made some different molecules, got some heat and energy out of it, and that is the chemical reaction. Okay, so that's kind of neat. Now, I don't know if you use propane or not, but you've probably read in the news where some people went to sleep with the propane heater on and they didn't wake up, right? Can you see why? I'm burning up 5 oxygen molecules every time I burn 1 molecule of propane. That's going to deplete the oxygen in your room. So if you're using propane, you really need to crack a window to where you're getting more oxygen coming in. No oxygen means you can't breathe, means you just kind of go to sleep and don't wake up. So be careful with propane. It's best used outside, but if you have to, then make sure that you've got some fresh air coming in, okay? Right here, I'd like to balance these equations. That's what we just did with propane and oxygen. And so let's see how we would do this. Right here is a chemical reaction. I've got P4O10 plus H2O yields H3PO4. Okay? Now we could go over here and look up P. We know this is oxygen. We know that's hydrogen. See if I can find P is right there. It's phosphorus. So I've got this phosphorus with oxides on it, but there are 4 phosphorus atoms, 10 oxygen atoms, 2 hydrogen atoms, plus 1 more atom of oxygen there. And when I get done, I want these. But what I can do is I can change how many of each molecule I have, and that's what we mean by balancing the equation. So I'm going to draw a little line out in front of each one of these, and we want to work out how many of each of these we need to have for this to work. Okay? So they've made a little table here. You can do this if you want. On the phosphorus, I had 4. So the P has got 4. Over here on the right-hand side, I got to have 4 P's, but I've only got 1. So I'm going to guess, and I'm going to say that there belongs a 4 right there, because if I had 4 molecules of H3PO4, then, you know, in the first one I'd have 1 P, in the second one I'd have a second one, third one I'd have 3 and 4. That would get me up to 4 phosphorus atoms there, and I'm starting out with 4 per molecule. So let's say that we end up with 4 of these. That will check this guy off. I need to make sure that the oxygens work out right. So right here I have 10 oxygens, and right here I have 1 more. That's 11. When I came in here and said, okay, I've got 4 of these, on the oxygens I have 4 per molecule. 4 molecules, 4 times 4 would be 16 is what I will need to end up with. Okay, well, I don't want to change the number in front of P4O10 because that would change the number of phosphorus and I'd have to come back and change this one. But let's see if we can find a number that would work right here. I've got 11. I need 16. So if I add 2 waters, then I would have 10 oxygens, and 2 oxygens would be 12. That's not enough. Let's go to 3. There's 10 oxygens. Here's 3 more. That's 13. Not enough. You see how you're just kind of playing with the numbers, and you want to get to the point where what's on the left equals what's on the right. And I think the number that we need here is a 6 in front of that. Let's check and see if that works. If I had 1 of these, I'll put a 1 there just to remind us, then my phosphorus is happy. And then I go about the business of fixing this oxygen. 4 times 4, because this number is kind of fixed now, 4 times 4 would be 16. I'm looking for 16 oxygens. Right here's 10 of them. I got 1 apiece in this. I need 6 more. So let's put a 6 right there. Now my oxygen is balanced. It's happy. I'll check all those out. If my hydrogen's happy, then I'm done. And if not, I got to scratch my head a little bit more. But let's see what we got. Here's 6 times 2 would be 12. I've got 6 2-packs. That makes 12. Right here I got 4 3-packs. That's 12. So now my hydrogen's happy, and that equation is balanced. Anytime you're going to mix P4O10 with water, I got to have 6 water molecules for each one of these, and that would make 4 H3PO4s. Okay? And now that is balanced. Here's a couple more examples real quick. I like to pick the weird things, like this SN right here. SN is 10, I believe. Where is that? Have I got one that shows big enough? I can't quite there. I think it's 10, like the metal 10. But let's just see what happens here. Right now I've got 1 on this side and 1 on that side, and that's balanced up. So if I don't double either one of those, then that would be happy, right? Now, if everything else can work with that, then we're good. If not, we'd have to come in and change this to a 2 and that to a 2 and fiddle some more. Let's see what's going on with oxygens. Right here, I'm going to change color too. I've got 2 oxygens here. I have none right here. This comes in 1 pack, 1 per water molecule. So I need 2. Let's put a 2 right there. If I had 2 waters, then I'd have 2 times 1 would be 2 on that side. And the oxygen would be happy. But does that work with my hydrogen? So right here, you can see there's 2 hydrogens right there. I got 2 on this side. Over here, though, I've got 2 times 2. There's 2 hydrogens in the first one, 2 in the second one. That makes a total of 4. So if I come in and put a 2 right there, then I'd have 4 hydrogens and 4 hydrogens, and that would be chemically balanced. There's a tin oxide. That should have been a little in. I've got 2 hydrogen atoms, 2 hydrogen molecules rather, for a total of 4 atoms. And that yields a tin and 2 water molecules. That's a chemical reaction that is balanced and would work out. One more here. I'd start with this sodium because it's kind of the oddball. Leave the oxygens and hydrogens alone. Start with something else. But right now it's good to go. So let's try 1 and 1 on that. That means that I would have 1 chlorine. So if I had 1 of these HCl, hydrochloric acids, then that would be good. You mix hydrochloric and sodium, it works over here. The only thing I got to worry about is this hydrogen on that. And see how I've only got 1 hydrogen on this side and 2 on that side? So that's not balanced. So I'd have to come in here and say, the only way I can get hydrogen is right here. Got to have 2 of them because these come in 2 packs. So let's double up on the this first thing here, 2 hydrochloric acids. Now I've got 2 hydrogens and 2 hydrogens. On the chlorine, I've got 2, I got 1 in each molecule of chlorine, so there's 2 on this side, but I've only got 1 on this side, so I'm going to have to double that right there. But now my chlorine is happy. Check your sodium. Right here, Na, I've got 2 of them. Over here, Na, I've only got 1 of them, so this needs to go up to a 2. If the table works better for you, then by all means do that. We've got sodium, we've got chlorine, we've got hydrogen, okay? On both sides. Those are all the pieces that I'm working with, but it's got to balance on both sides. And what they kind of did was to say before and after. You could say left and right, whatever you want, but we'll keep it before and after. And on sodiums, we only had 1 on each side before we started adding the number of molecules. Chlorines, we only had 1 on each side. Hydrogens, we had 1 on the right, on the left, and 2 on the right. And so you got to start fiddling with these numbers and say, well, this is going to have to be a 2, and that's going to put a 2 here, and that's going to change my chlorine number to 2. So that means I got to have 2 of these, and that's going to change my sodium number here to 2. So this has got to be 2. If the table way works better for you, but you just want to make sure that that you're not making atoms out of nothing, right? You can't do that. It's got to be there at the beginning and at the end to work out. And that actually gets us to the end of this thrilling discussion. Thanks for stopping by. Molecules are pretty neat. You were made of them. I am. Everything is. And they're all made out of atoms. And the atoms are made out of smaller things yet that we talked about back in the modern physics video. But it's pretty neat stuff. So thanks for stopping by. Have a great day.